3 sides. Start easy. What do we call a shape with 3 sides? A triangle. All right, we're off to a great start. 4 sides. This one's a little bit trickier. We use a prefix that means 4. This is called a quadrilateral. Quadrilateral for 4 sides. Rectangles and squares and parallelograms and trapezoids are all types of quadrilaterals. But the more general word is quadrilateral. 5. What is it? Pentagon. 6. Hexagon. 7 is a heptagon. 8. Octagon. And then I'll go ahead and show you the rest. These are going to come up less often. 9 is a nonagon, 10 is a decagon, 12 is a dodecagon. If we have more sides, which you don't come across, a 15-sided shape as often, but you put your number of sides and then gon. So if it's got 30 sides, you're going to call it a 30gon. But mostly we're going to stay in the realm of these. Okay, so we're talking about the area of regular polygons. So we talked about these are all the polygons. Right, these are the names for all the different shapes that we have. So now we're going to talk about what it means to be a regular polygon. You ready? Okay. Regular polygons. Here are some examples of regular polygons. A regular polygon is both equilateral and equiangular. Equilateral means all the sides are the same. Equiangular means all the angles are the same. So a regular polygon is when we have both. All the sides are the same and all the angles are the same. So right underneath that in your notes, you have some polygons there in front of you. Take a look at those 4. One of them is a regular polygon. Circle which one it is. So to clarify, you're looking at these 4. One of those is a regular polygon. Circle which one it is. And then see if you can classify the other ones with these terms of equilateral and equiangular. If it's not a regular polygon, then are any of them equilateral? Are any of them equiangular? So remember that for it to be a regular polygon, we should have all the sides the same and all the angles the same. So the one that is a regular polygon is this one. For the others, I'll just show this very quickly. You don't need to write all of this down. This one's equiangular, but not equilateral. Right? All 4 angles are all right angles, but the sides are not all the same. This one, the sides are all the same, but the angles aren't. This one, that's not equilateral or equiangular. If you remember our triangles, this is an isosceles triangle. Don't have all the sides the same, don't have all the angles the same. This one is my regular polygon. And if you count up the number of sides, we can more specifically say that that is a regular, what would be the name for that shape? One, two, three, four, five, 6 sides means it will be a hexagon. That is a regular hexagon. Okay, so that's all definitions. Now we're going to get to talking about the formula and how it gets made. So any questions on the definitions or terminology before we start diving into our formula? All right. This is not in your notes, so you just need to follow along. This is, if we had more time this year, this is something I would have you spend like 15 or 20 minutes working on and trying to come up with, trying to get you to come up with the method of how this area formula works. But here I'm just going to show it. And I'm going to show it for two of the shapes. I'm going to show it for the pentagon, and I'm going to show it for the octagon, so that you can see that the method works no matter which shape we're using. Here's the process. I'm going to go from the center. If you want the technicality, then the center here is defined as the center of a circle that this polygon is inscribed in. Okay? That's where the center of this pentagon is. And I'm going to draw segments out from this center. I'm going to draw them out to each vertex on the pentagon. So here's one. Here's two. All right, there are 5 vertices, so I should be drawing out 5 different segments. And that has created some shapes that you should recognize. What kind of shapes did I just make? Triangles. And how many triangles were there? How many of the triangles did I make? 1, 2, 3, 4, 5. 5 triangles. So I can show with a little bit of side that all of these triangles are congruent. They're all the same. And what that means is that instead of having to find the area of all 5 of those triangles and add them together, I can just figure out the area of one of the triangles, and then all the rest of the areas are going to be the same as well, so I can just take that area, multiply by 5, and I have the area of the entire pentagon. So in other words, I know the area. I know how to find the area of a triangle. Area of a triangle is 1/2 base times height. So here's my height, drop down perpendicular to my base. Notice how many triangles I created. Notice where the base ended up. Let's watch that happen again. Let's go to the octagon, and we're going to do it again. Same thing. Again, take a guess as to what shapes I'm going to make, how many of them am I going to make, and where the measurements are going to end up. Let's watch. Go from the center. I am drawing from the center out to each vertex on this octagon. There's one. Keep going here. Oh, hey, what shapes did I make? Oh, we made triangles again. How many of them did I make? Count them. 1, 2, 3, 4, 5, 6, 7, 8 of the triangles. So my area formula is going to consist of the area of the triangle times how many triangles there are. So let's talk about the pieces of that formula. When I do area of a triangle, I'm going to pick this triangle this time. Here's my height, dropped perpendicular to my base. The height of the triangle is not familiar to us. It's going to get a fancy name. I'll talk about it in just a second. Fancy name for the height of the triangle. But the base, we should be able to point out where it is. Where is the base in relation to my octagon? It is where? On the bottom, or in this case, it's on the top. In the octagon, where is it? It's a side. Right? It is one of the sides of this octagon. And remember that since it's a regular octagon, that means all the sides are the same. So it is whatever my side length is becomes the base of my triangle that I'm drawing. And you can go back to the pentagon and see that that happened with the pentagon too. What controls how many triangles I have? How many sides I have. And the reason that happens is because each of my sides is going to be a base of one of the triangles. So since I have 8 sides, I should wind up with 8 bases of my triangles and 8 triangles. So number of sides. So I'm going to have this 1/2 base times height formula, and then I'm going to multiply that by how many sides there are, because that's how many triangles I'm going to have. All right, so here comes the actual formula for you to write down. Oh, that's the activity we just did. Perimeter area for regular polygon. The fancy name for the height of the triangle is called the apothem. Remember I talked about drawing from the center being if I inscribe this polygon in a circle. So here's the circle I'm inscribing the polygon in. And so the diagonal lengths that I draw are each a radius of the circle, because I'm going from the center out to a point on the circle. So the height, the fancy name for the height is the apothem. And then we talked about how the base is just my side length. And then n is number of sides. Why is number of sides in the formula? Well, because remember that the apothem times the side length, that's my 1/2 base times height. So this is my area of the triangle. And then we talked about how the number of sides controls how many triangles I have. So that's why the formula looks the way it looks. It's on the basis of making these triangles and determining how many of them I have. Now, just so you know, this can make for some pretty fancy problems. We're not going to do the fancy problems this year, but I just want to show you what the fancy problems would look like. Just so you get a little teaser. Here's an example of what a fancy problem will look like. This is a pentagon, and so we would have our 1/2 ASN. This is our apothem, the height of the triangle. There are 5 sides in the pentagon. And then, we don't know what the side length is. But our fancy tools would be, let's use our knowledge of circles, since this is inscribed in a circle, to figure out what the central angle would have to be. And then let's use that angle and the side that we know and pull out some trig, which we have also studied, and use some trig to get our answer for that missing length. And then we would plug it into the formula to get our answer. Again, we are not going to be that fancy this year, but these problems can make for some nice review and looking at that knowledge about circles and that knowledge about trig to solve these. But we're just going to stick to the basic plug the numbers into the formula. So let's look at a couple of those questions over on the back. What's it called? Because the first bit of direction says name the polygon, so let's name the polygon. What's it called? That's a hexagon because it has 6 sides. So first off, we're going to write hexagon. Our number of sides, therefore, is 6. Then it's up to determining which length is which here that they're giving you. Well, the 14 is out on one of the sides of the hexagon, so that has to be my side length. And then the 12.1 is my apothem, because it is dropped down as a height from my onto the side here. If I drew out the triangle, let me draw out the triangle real quick. If I drew out the triangle, it would be the height of that triangle. So that is my apothem. And now we just plug those into the formula. One half my apothem, which is 12.1, times my side length, which is 14, times my number of sides, which is 6. And I can plug that in, and I would get I should get 508.2. And for my units, since we have an area, that should be units squared for area. The 6, remember 6 is our n, which is the number of sides that the shape has. So how many sides does it have? It has 1, 2, 3, 4, 5, 6 sides. So n is 6. Remember that's saying that if I drew all these triangles out, I would end up with 6 different triangles. So we're taking the area of one of the triangles and then multiplying it by 6 because there are 6 of them. That's how I get my total area. Other questions? All right, one more we'll do together, and then you'll do the rest on your own. Let's go down to number 4. I'll give you a little bit of a head start while I write down some information here. Write out some of the formula stuff. We have this distance here, and we are given this distance here. If I drew one of the triangles, it would look like that. If you lose track of counting your sides, then I had shown the system on the last problem, but sometimes I actually like to write out 1, 2, 3, 4 around my sides in this way, so I don't lose track of how many there are. Oh, there's 7, so that means this is called a heptagon, and it has 7 sides, so n is 7. Which one's our side length? Which one is actually labeling one of the sides of the shape? It's the 21.7. Here's one of my sides. It's 21.7. That leads to 22.5 to be my apothem, because it is dropping down the height of the triangle that I would draw. And the apothem is just a fancy name for that. So A is 22.5 times my side length, which is 21.7, times the number of sides, which is 7. I'm going to go ahead and put the exact answer without any rounding, which is 875 units squared for area. All right, and the rest of these I am leaving for you to do on your own. So that kind of acts as your homework assignment for today, is try the rest of these problems on your own, figure out the pieces, plug them in, get out your area,